Okay, present my window. Okay. All right, so I actually blew this up for presenting it to you guys tonight just because I wanted there to be enough space. It's one thing when you're just kind of working on it on your own, you kind of smash stuff in there, but since I was going to be presenting it to you, I wanted to spread it out a little bit. So this is the study guide for the final exam. It's on D2L. It is under, I think, exam reviews or something like that. There's also a key that's attached to this, and I will have a worked out key that I'm going to post tonight. There was some stuff I needed to add to it, but I did that this afternoon. So I'm just going to post the worked out key. So my goal for the review session today is just to go over any questions that you have. And then if you don't have any other questions, maybe just to go over some of the problems on here that I think you would have a harder time with, because I don't think I would be able to get through all of this in one class session, but you never know. So Catherine was asking about some examples of problems from chapter 7, which was test 2. Now, we did in chapter 7 a lot of work with rational expressions, functions, and equations. We were doing multiplying, dividing. We talked about applications. Let's see what else. That was a chapter 8 thing right there. We talked about finding the domain, simplifying with adding and subtracting. We talked about simplifying complex expressions. And then here we have some rational equations. So maybe I'll just start here on number 5, and then we can just kind of go backwards. And Catherine and Sonia, feel free to pop in if you have a question or if there's something in particular from this sheet that you want to go over, or if there was a particular topic that you had a hard time with on an exam. If you're looking at the tests in front of you, if you want me to go over something or maybe something like it, I have my book right next to me. I can find something like it really fast. Okay, so considering this chapter 7 material, and by the way, the first page of this is pretty much chapter 6. It's all just factoring. So we can come back to that if you would like. All right, but as far as chapter 7, example 5A is multiplying rational expressions. Remember that the whole goal here is that we want to simplify and multiply across. Before we do that, we're going to factor out each expression that makes up each part of this rational expression. So when we rewrite this, we're going to factor x squared minus 5x plus 6. And remember, that was, for whatever reason, one of those tricky ones where people tend to factor it incorrectly. Something about the 6 and the 5 together always throws people off. Let me zoom in a little bit more here. But make sure you're looking for numbers that multiply to 6 and add to -5. In this case, those numbers are -2 and -3. So if you're thinking 6 and 1, that can't be, because it would have to be +6, +1, or -6, -1, and those wouldn't add to -5. So we're going to factor this as x minus 2 times x minus 3. Remember that these are both minus signs because -2 times -3 is +6, and -2 minus 3 is -5. So just be careful with just these little things like you're factoring. They'll make a big difference. In the denominator, factor out the GCF of 2. And then in the next fraction, the numerator cannot be simplified. It's just x plus 2. And in the denominator, factor out the GCF of 2, and that leaves you with a factor of x minus 3. And then, once everything is factored, you can cancel. So, for instance, these x minus 3s are gone, and the x plus 2s are gone. And once you've canceled, you're going to multiply across. Whatever you do, don't try to do anything with these 2s. You cannot cancel them out because they're both in the denominator. You can only cancel between the numerator and denominator. So go ahead and multiply across. The only factor you have remaining in the numerator that is not 1 is x minus 2. I can tell I'm not using my hard lead pencil. Grab that. Excuse me. All right. X minus 2 in the numerator, and then in the denominator, the factors that you have left are just 2 factors of 2, and 2 times 2 is 4. And that is it. I guess I left a little too much space for that one. Any questions on A? You two? Okay. So for B, similar idea. However, remember that when you are dividing 2 fractions, you're going to invert and multiply. So we're always going to switch the numerator and denominator in that second factor. We'll turn into a factor and switch our division to multiplication. If you'd like, while you work on that, you can go ahead and start factoring. For instance, the difference of 2 squares, we actually haven't seen the difference of 2 squares in a while. We have x squared minus 9. Let me see. I'm constantly trying to figure out. Okay, better. All right, so the difference of 2 squares will factor to x plus 3 times x minus 3. Now remember, that was from chapter 6, section 5. So if you don't remember how to factor the difference of 2 squares, you're looking in 6.5, those notes from chapter 6, factoring binomials. In the denominator, you can factor out a common factor of x, and that leaves you with x minus 3. Now we're going to invert and multiply. So instead of writing a division symbol, I'm going to write a multiplication dot. And then I'm going to move this denominator into the numerator. And instead of saying it's 2x plus 10, I'm going to factor the 2 out and say that it's 2 times the quantity x plus 5. And then we'll factor the denominator, or I'm sorry, the old numerator, new denominator. Remember that this 4-term polynomial can be factored by grouping. So kind of up to you where you want to do this. I might just kind of pop this down to the next row here so that we can see what's happening with these terms. But we're going to factor xy plus 5x plus 3y plus 15. So remember, when you're factoring by grouping, you are grouping the first 2 terms together and the last 2 terms together. If for some reason you can't get it to factor, you can try to regroup your terms and see if that helps. Go ahead and take out your GCF of x in the first group. And in the second group, take out a GCF of 3. Now remember that you've done this correctly if each group now has a common factor, which is the case here, y plus 5. So then you're going to take out the GCF of each term, y plus 5, and that leaves you with x plus 3. Now remember, you can always check this by foiling it back together and verifying that you get back to what you started with, which is xy plus 5x plus 3y plus 15. So I'm going to go ahead and put this now back into the problem. So this is just a side note here for how we factored that by grouping. Okay, questions so far?
Does it matter like what if you put the x plus 3 first and then the y plus 5?
No, does not matter. Yeah, multiplication's commutative. You can multiply in either order. It means the same thing.
Okay, thank you.
Mm-hmm. All right, so go ahead now and cancel out your common factors. Now, in the numerator, you have an x plus 5. In the denominator, we have a y plus 5. So those two, we actually cannot cancel. And I know sometimes you're like, wait a second, it must be the case. Of course they cancel. That's the whole point. Well, not always. And if you actually, there is a key for this thing somewhere. I had it. What happened to it? Oh, it's in my other book. Hold on. But I'm going to refer you to it also. When you get done, you can always check your answers. It's also on D2L. So we have it in case something goes awry. All right, so go ahead and multiply across. And now when you get done multiplying, whether you want to multiply it all back together is really kind of depending on the instructions that you're given in my math lab. If it says to leave your answer factored, then leave it factored. And that's normally what we did with these problems, even with my math lab. So that leaves you in the numerator with 2 times x minus 3 times x plus 5. And in the denominator, you have x times x minus, oh, I forgot to cancel the x minus 3s. I was so focused on those 5s. All right. Well, you can cancel them out now. Better late than never. 2 times x plus 5 divided by x times y plus 5. And then you can go back. I'll put this on the screen. To your key. What is this, 5b? And you can verify that your answer is correct. Here we got number 5. B, you have 2 times x plus 5 divided by x times y plus 5. So you can always check these. This is the last page in the document that I posted for you on D2L. Okay. Leave it factored. That's fine. I would hate for you to expand it and end up screwing something up there. Any questions on 5B? I guess one thing I did want to make sure to mention, because some of you guys forgot it when we were in chapter 7, is that you cannot cancel these 5s. They're not common factors, they're terms. And they're not even really, I mean, isolated at this point. I mean, they're inside parentheses, but that's not the point. You cannot cancel these 5s. They're not common factors. They're just terms in the numerator and denominator. Now, if you had a common factor that was factored out of the parentheses, that would be something that you could cancel. But in this case, between 2 and x, you don't have anything in common. So let's make sure we understand when we can cancel and when we cannot cancel. That's a big one. All right, number 6. This was an application that we worked on in 7.6. We talked about this work problem. And in the work problem, you're basically just trying to determine how quickly 2 people can do a job together if you know how quickly they can do it on their own. And sometimes you're given different information, like this person can do the job in that much time. Together, they can do it in this much time. How long does the second person take? Something like that. But for this problem, you're being given information about 2 people. So Mrs. Smith balances the company books in 8 hours. It takes her assistant 12 hours to do the same job. How many hours would it take for them to complete the job together? And knowing that it takes one person 8 hours and the other person 12 hours, you should be getting a good idea of what at least you're expecting your answer to be. Like, for instance, if it takes Mrs. Smith 8 hours, then you wouldn't expect it to take any longer for them to do the project together. Like, if your answer was 9 hours, you'd be like, wait a second, she can do it by herself in 8. It doesn't make any sense that they're doing it together and now she's taking longer. So that's something that you should be thinking about as you go through these application problems. But remember, we made a chart for these and we put the 2 people in question in the chart. So Mrs. Smith, and we have her assistant. By the way, I did give you a problem like this on test 2. It might have even been the extra credit, but something like that. Can't remember if it was an actual work problem or not. But I know it wasn't. I know it was an extra credit at least. Okay, so we said something about the amount of time that it takes the one person to do the job. And then we had another column where we said the amount of the job that was done in 1 hour. Amount of job done in 1 hour. So for instance, if we know that it takes Mrs. Smith 8 hours to balance the books, then we know that in 1 hour, she's gotten 1/8 of the job done. And then for her assistant, if it takes 12 hours, we know in 1 hour she's gotten 1/12 of the job done. And then we'll have another row for having them work together. And that's what we don't know. Remember, your variable is always going to be responding back to this question that you're being asked here. How many hours would it take for them to complete the job together? That's the question. That's what your variable represents. The amount of time it takes them to do the job together will be X. That means that 1/x of the job is completed in 1 hour. Before we continue, do you ladies have questions about what we've done here so far? Okay. All right, so actually we can probably get rid of this. We don't have to have this column in our table. Let's go ahead and set up our equation. To solve for X, we're going to use the fact that it's Mrs. Smith will do 1/8 of the job in 1 hour, plus the 1/12 that the assistant will do in 1 hour is going to be equal to 1/x. And since we know these quantities are equal, we're going to be able to solve for X by solving this rational equation. And these work problems pretty much all go the exact same way. The only difference would be if you were given information about Mrs. Smith and together, and then you were asked to solve for what the assistant was doing, then those two terms would just be switched. Okay, so to solve this equation, remember you're going to multiply both sides of the equation, or every single term by the equation by the LCD. Now, remember, if you're having a hard time finding the LCD, it's going to combine constants and variables. So you know you're going to have an X in there, but you only have X to the first power. So you're going to use X to the first power in your LCD. And then you're also going to need to take the LCD between 8 and 12. Now, remember, when you're looking for your LCD, you're starting by checking the larger denominator and seeing if the smaller denominator is a factor. Now, I know that 8 is not a factor of 12 because I can't take 8 times an integer and get 12. So at that point, I'm going to take multiples of 12, like 24. So 12 times 2 is 24. 8 is a factor of 24. So that means that your LCD is 24x. Questions so far? Okay, wonderful. So let's go ahead and multiply each term by 24x. And when we do that, we're going to get those denominators to cancel out. I know that 8 goes into 24 3 times, so the first term will be 3x. I know that 12 goes into 24 twice, so the second term will be 2x. And then the x's will cancel on the right-hand side, and x divided by x is 1, so we'll just have 24 on the right-hand side. Now to solve for x, we have 5x equals 24. Divide both sides by 5. Normally, I like your answers as improper fractions. However, for these work problems, and a lot of times anytime you're dealing with an amount of time, we don't usually talk about hours in improper fractions. We normally would talk about hours, like 1 1/4 hours or 1.25 hours or something like that. So a lot of times you're going to be asked for mixed numbers for these, which is weird because normally you're not wanting to use mixed numbers. But for something like this, you do need a mixed number. 5 goes into 24 4 times with 4 left over. And you get 4 4/5 hours. And then that makes sense to me. If Mrs. Smith is doing the job by herself in 8 hours and the assistant takes 12 hours, then almost 5 hours. Sounds about right. So working together, they're going to cut that time down. Any questions about number 6? Okay. All right, then, continuing on with some of these topics in chapter 7. Number 7 is actually a variation problem. Do you guys want to do the variation problem? Catherine, Sonia?
Can we do that actually?
Sure.
Thank
we
you.
will do it. No problem. Okay. The amount of pollution, P, and I'm going to start writing this down as I read. The amount of pollution, P, varies directly with the population, N, of people. Varies directly means you're going to have P equals K, N. Remember, when you vary directly, whatever is behind your equal sign is going to get multiplied on the right-hand side. When the variation is an inverse variation, focus. When the variation is inverse, then your variable will go into the denominator. But no matter what, remember that K, your constant of variation, is always in the numerator. So pollution varies directly with the population N, looks like this. So if it was inverse variation, you'd have P equals K over N. But since it's direct, you have P equals Kn. There is another variation problem at the end here that we could do also, if you want to do that. Kansas City has a population of 460,000 and produces about 270,000 tons of pollutants. Find how many tons of pollution we should expect St. Louis to produce if we know its population is 319,000, round to the nearest whole ton. All right, be careful here because we're talking about population and pollution. They're both P's. Make sure you know which one's which. P is the amount of pollution. The information you're given is that Kansas City has a population of 460,000. The population is actually represented by the variable N. So go ahead and fill this in. N will be 460,000, and it produces about 270,000 tons of pollutants. That is P. So just little things like that to watch out for with these problems as far as the choice for variable is concerned. All right, now you're going to solve for K. So we're going to divide both sides by 460,000. My calculator up here. So we'll have 270,000 divided by 460,000. And I'm just going to leave this answer in my calculator, I think. I'm going to write on here a slightly truncated version maybe. But this is giving me the value for K. So I know the constant of variation is 0.5869565,217. Okay, I wrote the whole thing. We're going to use that now in the next step to figure out how many tons of pollution we should expect if the population is 319,000. So going back to our original equation, how many tons of pollution, which is P, should we expect if the population is 319,000? So we're going to go ahead and use that value, the 0.5869565,217 times 319,000 for the population. Now, if you still have this number sitting in your calculator, then you know that in order to find P, the number of tons of pollutants, you can just take this value in your calculator and multiply it by 319,000. If you rounded this in the last step to 0.59 and then you multiply it by 319,000, it's probably fine. I mean, let's say that you had rounded it 0.59 times 319,000. You're still going to get close, but I don't really know if, I guess if we're rounding to the nearest whole ton, yeah, that would, my math lab might have some background answers programmed for something like that. But really, your answer should be this one. 187,239.1304. And if we're rounding to the nearest whole ton, in this case, we're rounding down, or not down, I guess we're just going to truncate this last part, just because 1 is less than 5. So we have 187,239, and this would be tons. Okay. So that's a variation problem, not too crazy, just because it was a direct variation problem. Any questions on that one? Okay. Let's see. Number 8. Finding the domain of this function. This is actually supposed to be very easy to do. However, on exam 2, a lot of people missed this one, just either left it blank or didn't know what to do. When you're finding the domain of the function, what you're looking for are the values of x for which the function is defined. In order to find those values, you need to find values of x for which the function is not defined. What that means is you need to find values of x that would make the denominator 0. We can't divide by 0. If you divide by 0, your function's not defined. So take your denominator and set it equal to 0. And we're going to find values here, or in this case, a value that we need to exclude. And this is going to help us find our domain. So when you're looking for the domain of a function, you're just focusing on the denominator if it's a rational function. We talked a little bit about doing this for radical functions, and in that case, we were just looking at values such that the radicand was greater than or equal to 0. If you have a rational function, which means a polynomial in the numerator and denominator, just set the denominator equal to 0 and exclude any of those values. Do this however you would like. If you want to factor it, you can do it that way also. And then -6 divided by 2 is -3. So we know that if x equals -3, the denominator will be 0 and the function will not be defined. So if you want, you can just say cannot equal, and then you know that x can't equal -3. And some people did this on their test, and the instructions on your exam for test 2 said to write your answer in interval notation. What that means is you need to actually figure out the domain of the function. So what values are acceptable? Well, that's any value that's not -3. So that means I can pick any value from -infinity all the way up to, but not including -3. And then once I get past -3, any value beyond that is also fair game. So that is the domain of the function. Are there questions on number 8? Okay. All right, number 9. This is one of the trickier topics in chapter 7. In this problem, we are adding and subtracting rational expressions, subtracting here specifically, with unlike denominators. Remember that in order to add or subtract two fractions, they need to have the same denominator. So for something like number 9, first, some of you might be noticing right away that this first denominator is a perfect square trinomial. If you notice that and you want to factor it that way right away, that's fine. If you don't notice that, no big deal. We can factor it the old-fashioned way. The two numbers then multiply to +1 and add to -2 are -1 and -1. So you'll have x minus 1 times x minus 1 in the denominator of the first term. Now, this is good because you can actually now cancel out a factor of x minus 1 in the numerator and denominator. Now, a lot of times we don't want to do that because the whole point is to build our fraction up and then simplify it back down. But because this fraction already has x minus 1 in the denominator, you just need these two to have like denominators. And once you cancel out this one, they do. Now, another thing that students tend to miss on a problem like this is that when you take x minus 1 and divide by itself, that simplifies to 1 over 1. The numerator here is not 0. The numerator is 1. So when you rewrite this, you have to account for the fact that there's still something non-zero in the numerator, and that something is 1. All right, before I proceed, questions here? Wonderful. The other thing that tends to go wrong here, and it went wrong on the Chapter 7 test, is that anytime you have a minus sign and there's more than one term behind it, you must distribute that minus sign to all of the terms behind it. So what this looks like when you rewrite it as one fraction is 1 minus the quantity x plus 1. And then you can write both of these as one fraction. And now you're forcing yourself to distribute this minus sign into the parentheses. So now you have 1 minus x minus 1 over x minus 1. Now 1 minus 1 is 0. So you're left with negative x over x minus 1. This is good. Technically, you could leave the negative in front of the fraction. That's fine. You could put it in the denominator if you want to. That's fine. This is done. And I also want to make sure that you know you cannot cancel these x's because you can't factor an x out of the denominator. You can't cancel it. It's not a common factor at this point. You would have to have that factor in common in both terms, and you don't. If it's not a common factor, you can't cancel it out. Questions on number 9. All right, so that was a good one to do. And then for simplifying complex fractions, I gave you guys a bunch of examples of these in 7.7. Maybe I should be marking the section that these came from as we go through, if I can remember. Let me see. This was 7.2. I know that, number 5A. 5B was also 7.2. I want to say this was 7.6. This was 8.4. Find the domain. 7.1, 7.4 for number 9. If you need to go back to your notes and look, I'll have those there for you. I'll try to do that for all of them. All right, so this was 7.7. This is a complex fraction. I had given you 2 different methods for doing this. One of the methods was for in case you just had one term in the numerator and one term in the denominator. They would still be fractional terms, but if that was the case, you could just invert and multiply. However, you can't just invert and multiply here without just getting one fraction in the numerator and one in the denominator. You can do that if you want. I think it's a little more work. What I like to do is multiply each term by the LCD. That means you need to look at all of the denominators and find the LCD. Here you have an x, there you have an x squared. Remember, your LCD has to include the highest power that you see in any one denominator. Then you also have an x down here. So x squared will have to be your LCD. You also have a 1, but big deal. So your LCD is x squared. Remember, the whole point is that when you multiply by the LCD, you want the denominators to cancel out. So if you were to multiply by x instead of x squared, well, you'd still have a factor of x left over in that denominator here. These two would cancel, but that one wouldn't. So We have to make sure that we're including everything that we need to in that LCD. I'm going to write this again just so I can make it very clear when I'm multiplying here by x squared. But every single term is going to get multiplied by x squared. And then we'll simplify it out. And the goal is that when we are done, we will not have a complex fraction anymore. And we'll just see what we need to simplify. So between the x squared and the x, you just have an x left over. The x squareds in this term both cancel out. That just leaves you with a 3. In the denominator, you have 5x squared. And in the second term, the x squared and the x just leave you with 1 factor of x. Now, technically, yes, you can factor an x out of the denominator. If the instruction on my math lab says to leave your answer in factored form, then you should do that. However, there's actually nothing that you would be able to gain from that other than just following the instructions. So if that was the instruction, fine, you can write it like that. But there's nothing that you can cancel out, so it really wouldn't be helping you out that much. So this is fine. And that would be something where if they asked you to write it like this and you wrote it like that, but there was nothing that you could cancel, I would give you all the points for it anyway on your final. Okay, so questions on number 10? The only other thing that was from chapter 7 that we haven't talked about was rational equations. Now, something like this we saw in chapter 11 when we were talking about 11.3 being quadratic in form. Something though like 11a, this was covered in 7.6. We talked about proportions. Technically, this was also covered in 7.5, solving rational equations. But remember that the 7.6 part was discussing specifically proportions. A proportion is when you have an equation with rational expressions where you have only one term on each side of the equation. When you have a proportion, I'm going to write it down, you can cross multiply. So this is a special case where for a proportion, you just have one term on each side of the equal sign. So go ahead and cross multiply. You'll have, don't forget your parentheses, 5 times the quantity y plus 2 and 4 times the quantity y plus 1. And then you're just going to distribute and solve. So 5y plus 10 equals 4y plus 4. And then subtract 4y from both sides. Oh my goodness. That leaves you with y plus 10 equals 4. And then you're going to subtract subtract 10 from both sides. Let me rewrite this over here. And you get y equals -6. Remember, you need to verify that the value that you get when you solve a rational equation does not make the denominator 0 in your original equation. So an answer like y equals -1 or y equals -2, you would have to get rid of because those can't be included. However, y equals -6 does not violate the domain of either one of those rational expressions. So y equals -6 is fair game. Check it if you want to. I'll leave that up to you. Questions on 11a? Now 11b is a little bit more interesting, but still not a whole ton going on here. When you multiply by the LCD, we're looking at these fractions and trying to find the least common denominator. You have x minus 3 in 2 denominators, and then you have a 2 in the other denominator. So your LCD is going to be 2 times x minus 3. So we're going to multiply each term by the LCD. 2 times x minus 3 times x over x minus 3 equals 2 times x minus 3 times 3 over x minus 3 minus 2 times x minus 3 times 3 halves. So again, remember with these, I know they can be tricky to rewrite. Everything stays the same except each one of these fractions gets multiplied by the LCD. So when you cover up that LCD, well, everything should look the way it originally did. So you've got the left-hand side, the first term on the right, and the second term on the right. And then you just start canceling. And you see what's left and simplify. So on the left-hand side, you have 2x. On the right-hand side, 2 times 3 is 6, minus 3 times the quantity x minus 3. Make sure that 3 gets distributed into your parentheses. 2x equals 6 minus 3x plus 9. Do this in any order you'd like. 5x equals 15. X equals 3. Now, you're thinking, great, I'm done, awesome. Don't put a circle around it. Because notice that if you let x equal 3, well, guess what? Now you have a situation where your rational expression is undefined because 3 minus 3 would give you 0 in 2 of these denominators. That cannot be. So we're going to say that 3 is not in the domain. So no solution. And you can use the symbol or you can just say no solution. But don't say x equals 3. I like to see the work. I like to see that you found it. You get credit for doing that. But I mean, if you were to just say no solution from the beginning, how could I give you any credit for that? But show me your work. Show me that you found a proposed solution. You don't have to show me your check. I mean, clearly you can eyeball it and notice that that would make your denominator 0. Questions on that one? Okay, now that was 7.5. All right, we did a little bit of solving for variables, not a whole ton. This is another thing that you would have seen in chapter 7. I think it was either 7.5 or 7.6. A little bit of both, maybe. Maybe it was 7.6, but it uses still the idea from 7.5. When you're solving for a variable, some students find this a little trickier just because you don't have numbers that you're working with. But yes, I do remember walking around. You guys, we did a bunch of these in class. I couldn't remember if this was something we lightly touched on. We did. And I remember that when we did an example like this, some of you guys multiplied each term by g, and then others of you first subtracted r. And then you got 2 answers that looked kind of different. So if you want to subtract r from both sides, you can do that. Just make sure that you don't try to somehow combine those. And you can rewrite that as n minus r equals v over g. Now, if you're trying to solve for g, you're still going to have to do a little bit of work with multiplying both sides of the equation by g. There's really no way of getting around that. If you're trying to solve for a variable that's in the denominator, you have to get it out of the denominator using multiplication. So let's say multiply each term by g. And really, the way that you need to write this, I'm going to write this one more time just so that it's clear in the notes where it came from. When you multiply on the right, I guess you just multiply it once. On the left, it's possible just to multiply that entire expression on the left by g. If you're going to do that, you need to use parentheses. Well, then you could say that v equals g times n minus r. And that's okay, but pay attention to the instructions, whether it says to leave your answer in factored form. Just remember, if you do this, you have to use parentheses. Some of you guys might, though, from the start, multiply each term by g, and then you would get n times g equals r times g plus v. And that's what happens when you multiply every term by g. Now, this is a little bit trickier now because to get g by itself, you can subtract rg from both sides, and g minus rg equals v. And then the only way to get g by itself would be to factor it out, which actually looks exactly the same. So it kind of just depends. This could also look like that. Several different ways that you could see this. And depending, you might have even used a slightly different solution process and gotten something that looked slightly different. But yeah. Oh, gosh. Why am I not solving for g? Guys, I'm losing it. I was solving for v. We have to get g by itself. Going back. Solve for v, solve for g. V rhymes with g. I don't know. Can't explain that to you. Don't solve for v, solve for g. Okay, since we were already on this one, in order to get g by itself, if you were to multiply all three pieces of this by g, that's fine. We can still use this work. You would still get this expression, which is fine, but to get g by itself, you would have to factor it out and then divide both sides by n minus r. And then you would get g equals v over n minus r. Not solve for v, solve for g. And you can see here how you'd get the same thing to happen just by dividing both sides by n minus r. So yeah, same answer. Questions on 12? Sorry about that. Okay. Let's do number 13. We did one similar to this in class. It's a good one. A cyclist rode the first 20-mile portion of his workout at a constant speed. For the 16-mile portion of his workout, he reduced his speed by 2 miles per hour. Each portion of the workout took the same time. Find the cyclist's speed during the first portion and find his speed during the cool-down portion. Remember that we used the formula D equals RT when solving these distance and motion problems. We did some with boats. We did some with cars that were either traveling in the same direction or different directions. We had some with trains. I think we had some with planes. When you're in trig, you'll be looking at planes heading at each other from specific angles, but not here. Right now, we're only working with the formula D equals RT for this kind of problem. And this was also from 7-6, the applications section. So I'm going to remind you of how to fill out your D equals RT chart, but we did charts pretty much for all of these. So he's got two portions of the workout. He's got the 20-mile portion and then the 16-mile cool down. So I don't know, you can call this first portion and second portion if you want to just do it that way. That seems more clear. All right, so you were given specific information regarding the rate. You were not specifically given how fast he was going. Remember, rate refers to how fast you're going. But it did say that for the second portion, he reduced his speed by 2 miles per hour. So whatever he was going the first portion, we don't know. For the second portion, he was going 2 miles per hour less than that. So that's really the key information that you need to start out with this. We'll make this into a little chart. Now remember, your question is going to lead you to your variable. Find the cyclist's speed during the first portion, that's your x, and find the speed during the cool down portion. You're also given some information about the fact that each portion of the workout took the same time. That means that you need to find the time that he was cycling in the first portion and set it equal to the time that he cycled in the second portion. You know that the distance for the first portion was 20 miles, and the distance for the second portion was 16 miles. Remember that if d equals rt, then we can take d over r to get to t. So d over r is 20 over x for the first portion and 16 over x minus 2 for the second portion. Each portion took the same amount of time. So set those quantities equal to each other. Questions so far? Wonderful. It's a proportion. Cross multiply to solve it. Make sure when you cross multiply, you're putting parentheses around x minus 2. Okay, now solve for x. You'll have 20x minus 40 equals 16. Oh, I forgot the x. When I cross multiplied, I was so focused on telling you to put parentheses around here. 16x equals 20 times x minus 2. All right, that makes more sense. Minus 16x, and you get 4x minus 40 equals 0. 4x equals 40, and x equals 10. Sorry, I'm running off here. So if x is 10 miles per hour, then that means that his rate on the second portion was x minus 2. 10 minus 2 is 8 miles per hour. So I don't care. You already have your table labeled, so this is fine. Questions on number 13? By the way, I would highly encourage you, especially for sections that maybe you're not as familiar with or things from chapter 7 that maybe you haven't used in a while, to go through your notes. Go through test 2. If you'd like, you can go on to D2L, and I have a whole section of, well, it's not a whole section anymore because we only had 2 tests in class, but there's a blank version of test 1 and test 2. If you want to redo them, you can do the blank version, and it'll be like doing it from scratch, and it's been so long you won't remember it. And there are also keys on D2L for those tests. So use all of those resources. You can do the blank test and then look at the key that's on D2L. Go through your notes. These are all things that are at your disposal to help you study for your final exam. All right, I think that was all from chapter 7. Number 14 is chapter 10. Let's see, domain and range of a graph. Should we talk about that? Yeah, we probably should. Number 15. We could do 14 if you want. Maybe we'll come back to it. That is more recent. I guess I was thinking more of focusing on the older stuff, unless you guys had specific questions. For something like 15, talking about the domain and range, remember that the domain is talking about what values the graph covers horizontally. The range is discussing the values that are covered vertically. So when you're looking at the domain of the function, remember you're looking at the x values. Now it's a little bit difficult to see on here. Not terrible, but I guess I could zoom this in a little bit more. It's gonna go berserk on me. That's a little bit better. When we're talking about the domain, we're looking at the values that the graph covers horizontally. I'll have to write this. And what we're seeing on the graph is that horizontally, we're starting here at 0 and then going up to x equals 60. So that's what's corresponding with what you're seeing up here on the graph. So if you need to make a little dotted line to see where everything lines up, that's fine. But it looks like you have a point listed at 0 and then about 75. And it's kind of hard to tell because you don't have open and closed circles here. On your exam, this will be a little bit more clear, but this was made by the department, and I don't know. Let's put little dots on there just so it's clear, little closed circles. So we're going to start our domain at 0, and I'm going to use a bracket and not a parenthesis. And I'm using a bracket because it looks like the point actually exists at 0.75. So I'm going to use the bracket for 0, and we're going all the way up to x equals 60, and we have points graphed up to x equals 60. Now, once we get past 60, there's nothing there. So 60 is going to be the largest value in our domain. And again, it looks like there's a point there. I'm putting a closed circle on it, so there definitely is a point there. So you can go ahead and put a bracket on that at 60. For the range, same idea, but the range is covering y values. So when we're talking about the values that the graph is covering, we're starting at y equals about 75. If you can kind of see how we're going up here now to 100. So we have points that start here at about y equals 75, and then they go up to y equals 100. Sorry, my dots are a little bit low. I don't want that to be misleading. So we're going to use values that go from 75 to 100. And use a squared off bracket. I wonder what your key used. Yeah, they also use squared off brackets. Okay. Questions on this one?
I actually had a question.
Mm-hmm.
So if the line was continuously going without that dot, would that be then parentheses?
If the line was
Like if it kept going instead of having that dot over there?
if it kept going, then you would have to keep the values going.
Okay.
The instances where you'll see that the domain or where you won't have a squared off bracket and you'll have a parenthesis would be if there was an open circle.
Okay.
So something like this would indicate that the value doesn't actually exist at 60, 100. So if there was an open circle here, then both of these endpoints would not get squared off brackets. They would get parentheses.
Okay, that makes sense.
Yeah, that's what you would see.
Okay, thank you.
You're welcome. Anything else on this one? Okay. All right. For number 16, I put, don't worry about this. You're not going to see something like that on your final. We didn't really do anything like that in class. There is a graph of a rational function that's a little bit more current, so I'm going to skip past that for now. And this was all stuff from 8.1 and 8.2. I don't know. Can you guys hear my children screaming in the background? I never know. Like, there's so much screaming. And the baby has recently learned to scream, and now there are like 2 people screaming. My oldest son doesn't scream, but it's very distressing. And I'm sure that when they're outside, the neighbors are just like, what is going on at that house? They're just screaming all the time. It's terrible. All right, number 20. All right, I did think that this was important. We did briefly talk about this in 8.1. So let's talk about the difference between the dependent and the independent variable. A study analyzed the effect of a medication on cholesterol levels. The higher doses of the medication were associated with lower cholesterol levels. So if you're thinking about the fact that you give somebody a medication And no matter what you do, their cholesterol levels go down. So the cholesterol levels are dependent on the amount of medication that you give that person. And that is an independent value because you have a choice of how much medication you're going to give them. However, once you give them the medication, their cholesterol levels will become lower proportionally. So in this case, the independent variable would be the dosage of the medication or something of that nature, because that's something that you control. And then for the dependent variable, we're talking about cholesterol levels. So these are going to depend on the medication. So that's number 20. So something small like that, but I just wanted to make sure we understand the difference between an independent and a dependent variable. All right, what else is in here then? All right, some of this stuff is from chapter 9. And that is the stuff that we covered right before spring break and right before we went on lockdown. I taught you guys all of this stuff in the classroom. So maybe this chapter 9 stuff would be good to go over here. And then if you wanted to go over some of the later stuff, that would be fine. All right, so we have an absolute value equation. Remember, what you want to do is isolate the absolute value expression. Okay. So you'll have 3 times 2x plus 4 equals 9. I swear my husband is with them. They're not just like screaming downstairs unaccompanied. They really do have an adult with them. I don't know what he's doing, but okay. We're going to isolate the absolute value bars. So go ahead and divide both sides by 3, and you get the absolute value of 2x plus 4 equals 3. Now, you're halfway done, because remember, when you're solving an absolute value equation, you need to account for the fact that the expression inside the bars could have been negative. When you take the absolute value of a negative number, you get a positive number. So we need to account for the fact that 2x plus 4 could have been 3, or it could have been negative 3, because the absolute value of negative 3 is also 3. So when you're working on these, you must include 2 variations. We'll have 2x plus 4 equals 3 and 2x plus 4 equals negative 3. Okay, so subtract 4 from both sides and you get 2x equals negative 1, x equals negative a half, 2x equals negative 7, x equals negative 7 halves. So for these absolute value equations, you should be getting 2 answers. Questions on that one? Okay, let's look then at an absolute value inequality. So for something like B, we're looking at an instance where the absolute value of 2x minus 5 is less than or equal to negative 7. And you don't even have to do any work on this one, because absolute values can only be positive, or they could technically be 0. But absolute values are distances. They cannot be less than or equal to negative numbers. So in this case, we would have to say no solution, because absolute value cannot be negative. Okay. Now C, this is an instance where we have the absolute value of x minus 3 plus 2 is greater than 5. When that occurs, you're going to remove the bars. As long as the absolute value expression is isolated, you're going to take the bars off for 1 half of this. For the other half, you're going to switch the direction of the sign and make the right-hand side negative. So really similar to what we did with the equation in A, the difference is that when you have an inequality, you got to flip the inequality. Now remember, this was our procedure for when we have a greater than sign. For D, we have a less than. So for D, we have a little bit of a different procedure. This was from 9.3. 9.3. Yes, this was that day I was getting observed. That was from 9.2. Okay, so we're going to solve each one of these inequalities on its own. So you'll have x over 3 is greater than 3, which means x is greater than 9. And remember, we write these as OR problems. Again, subtract 2, so you'll have x over 3 is less than -7. Multiply both sides by 3, and you get x is less than -21. And these are ORs. So if x is greater than 9 or x is less than -21, well, x is greater than 9 gives you that. X is less than -21 gives you this piece. And remember, you can always graph it if you're not sure. And you're pretty much always asked to answer in interval notation for these. Does anyone have a question on C? Okay. D. All right, this is an example where you have a less than. So we had a slightly different procedure. For something like this, we took the negative value of what was on the right-hand side, and then we rewrote this as a 3-part inequality. Technically, you could do the same thing we did in C and then change it to an AND problem, but this is the way we did it in 9.3, and I want to make sure we understand the difference. So if it's a greater than, it becomes an OR problem. If it's a less than or a less than or equal to, we turn it into a 3-part inequality. And then you just solve for x. So add 5 on all 3 parts. -2 is less than or equal to 2x, which is less than or equal to 12. Oh, not divide by x, divide by 2. And you'll get -1 is less than or equal to x, which is less than or equal to 6. And then your interval notation follows directly from that solution. So that's been a while. Glad we talked about those. Questions on D? Okay, these are much more recent from chapter 10. Let's see. Also chapter 10. Let's see, this was 10.6. That was 10.5. 10.6. 10.7. 10.7. So this is all chapter 11. This is a bunch of solving quadratic equations. Don't worry about number 36. 36 is about writing our own quadratic functions. I don't need you to do that. 37, we didn't actually get a chance to talk about exponential functions, so don't worry about 37. And some of these last problems do discuss chapter 12 material. An exponential function, by the way, is one where you have a variable in the exponent. So that's an exponential function. So that means no 38, but 39 is a variation problem. Maybe we should do 39. Suppose that Q is jointly proportional to R and the square of S. Yeah, we can do 39. from 8.4. Okay. Suppose that Q is jointly proportional to R and the square of S. Now remember that we had different definitions for what it meant to be proportional. And jointly just means that you're multiplying these proportionalities. Sometimes you could have combined variation, in which case you'd have two different kinds going on at the same time. But you don't see that here. You just have that Q is jointly proportional to R and the square of S. And that's how you would write this variation equation. That we will solve. We're going to go ahead and use this information just like we did in the other 8.4 problem to solve for Q. If Q equals 24, when R equals 3 and S equals 4, focus on that, then find Q when R equals 2 and S equals 3. So if Q is 24, when R equals 3 and S equals 4. So let's go ahead and plug that in to our proportionality equation, and then we'll simplify to find K. Once we find K, we'll rewrite the equation with K and then solve for Q. So 3 times 4 squared is 3 times 16, which is 48. Divide both sides by 48, and you get K equals 1/2. And then go back and say Q equals 1/2 R S squared. Now find Q when R equals 2 and S equals 3. And then we'll just multiply on the right-hand side. 1/2 times 2 is 1, and then 3 squared is 9. So that was number 39. Questions on 39? Let's see what else there is. 40 is the graph of an exponential function. You are not responsible for that. Some of you, I'm sure, could figure it out. This is what we did in 11.6, number 41. Number 42 is another exponential function where you have 3 to the x minus 1. Is that the last one on there? I don't know why I thought that there were more. No, that is all. Okay. All right. Now, I did everything from chapter 7, and I did some things from chapters 8 and 9. It's up to you. I'm going to post the key to this review that's already completed. Did you want to go over anything else from this review sheet?
Can we do the first one, please?
Okay, so number 1, factor. You have 8x cubed plus 27. And good, we'll do number 14 after this. 8x cubed plus 27. This is the sum of 2 cubes. And you have a formula for this, and luckily it is in your notes. Remember that this was from section 6.5. If you don't remember, I'm reminding you now. Your sum of 2 cubes, and remember we had an acronym for this. It was the SOAP acronym. It was same, opposite, always, positive. So A plus B, same, because it's a plus. Opposite, A minus AB, always positive, was plus B squared. So same sign, opposite sign, always positive. In this case, we just need to figure out what A and B are. So 8x cubed is really just 2x quantity cubed. We can let that be A. And then, of course, 27 is 3 cubed. So if you want, you can let A equal 2x and B equals 3. if you're using this formula, which you will be using. Just it kind of depends on, do you want to label it like that, or do you just want to plug it in? And that's up to you. All right, questions so far? Okay. Well, wonderful. A plus B then. So A would be 2x plus B means plus 3. Oh gosh, you know what? I forgot the a squared in my formula. You guys, I'm falling apart here. It's a squared minus ab plus b squared. Those pieces are always squared. Sorry about that. I knew that looked funny when I wrote it. All right, so we're going to take a squared. We're going to simplify that in a second. Minus ab plus b squared. And then we'll simplify. Two x plus 3 times, and don't forget, when you're squaring 2x, you must also square the 2. Don't just write that as 2x squared. It's actually 2 squared and x squared. 2 squared times x squared is 4x squared. And then minus 6x plus 9. And that is how you factor the sum of two cubes. Question on that one? Okay. So the factor by grouping, we did another example where we factored by grouping earlier. This is just, so that was what, 6.2. This was 6.4. This over here was 6.6. Does anyone want to do anything else on the first page before I do number 14? Sure, I'm checking my chat. Feel free to put numbers in the chat too if you want to work on them. Okay. All right, number 14. This was from chapter 10. Simplify and express your answer with all positive exponents. So we are going to start, I think the best way to start this, and there are a couple different approaches, but I would probably make all the negative exponents positive, and then I would start working with simplifying them. But that's up to you. You can go ahead and start with the quotient rule now if you'd like. I'm going to go ahead, though. I'm going to leave the x squared in the numerator where it is, and I'm going to leave the x to the 7th in the denominator because those are both positive exponents. But the y to the negative 5th and the y to the negative 7th, those I'm going to flip or switch just to make their exponents positive. So now I'm going to have y to the positive 5th in the numerator and y to the positive 7th in the denominator. So remember that if you want to switch the exponent from negative to positive, switch the expression's placement in the fraction. And then we're also going to move this x to the negative 3rd into the numerator. I'm sorry, not x to the negative 3rd, z to the negative 3rd into the numerator as z to the positive 3rd. And then we're going to work on simplifying those exponents. Any questions here? Okay. Now, a couple different ways of doing this. Essentially what you're doing is using the quotient rule for exponents. I think that's just what I'll do. This says that if you have a to the m over a to the n, you have a to the m minus n. So we'll subtract the exponents and just keep the base. And we can do that with all three of these expressions. Really, I guess the cube doesn't need to change. But if you wanted to apply this rule directly, you could think about just splitting this into 3 fractions. You don't have to do this, but you might find this looks easier for you if you're planning on just applying the quotient rule. And then to do that, we'll have x to the 2 minus 7 times y to the 5 minus 7 times z cubed. And then we'll simplify. X to the negative fifth times y to the negative second times z cubed. And then once you have this simplified so that you just have one of each base to a power, now you can write your answer so that it has only positive exponents. Normally an answer is not considered simplified until all the exponents are positive. So z cubed can stay in the numerator, but x to the negative fifth will move to the denominator as x to the fifth. And y to the negative second moves to the denominator as y to the positive second. And that is number 14. Anything else you guys wanted to cover from the review sheet?
I saw like a problem that on the first page. I'm not sure what number it was, but there was one that I was wondering if we can do.
Which one was it?
The first page. So that was number 2.
Oh, number 2. Okay, the factor by grouping?
Yeah.
Okay. All right, so let's do the factor by grouping. Let's go ahead and combine the first 2 terms into one group and the second 2 terms into another group. Now, remember, if you try the factor by grouping and it doesn't work because you don't get common factors, you're going to have to rearrange the terms and try again. I think these will be good, but you never know. So let's go ahead and take the GCF out of each group. In the first group, you have a y squared in common. When you factor that out, that leaves you with x minus 7. Now remember, if your middle term, or the sign on your third term in this case, is negative, you need to factor out a negative GCF. So between 4 and 28, the GCF is 4, but you need to factor out a negative 4. Now that's going to make a big difference because when you factor negative 4 out of positive 28, you're going to end up with negative 7. Now, partly you'll know that you should end up with that because you want to match this, but you don't want to blindly match what you did in the first term. So make sure that when you distribute this negative 4 back in, you get back what you started with. Questions here? Okay. Now, you're being asked to factor completely. Now you have 2 terms. Take the common factor of x minus 7 out of each term. That leaves you with y squared minus 4. And again, you can rewrite this as y squared minus 4 times x minus 7. The order doesn't matter here. When you're multiplying, those factors can be written in either order. Now, you're not actually done yet because you have a difference of 2 squares here. So don't forget to factor your difference of 2 squares. And now it's all the way done. All right, what else? You still have like 14 minutes if you have other problems you want to do.
Can we possibly do number 4?
Mm-hmm. How about I remind you how to do number 3 just in case it's been a while, and then we'll do number 4 also since we have some time.
Yeah, that would be great.
Okay, good. So for number 3, remember that we have a specific situation here depending on whether your lead coefficient is 1 or not 1. In this case, because A is 6, it's not equal to 1, you have to use factor by grouping. So must factor by grouping. In order to factor by grouping, you need to make 4 terms for your polynomial. In order to determine how to split up your middle term, you're going to have to figure out what 2 numbers multiply to A times C and add to B. So 6 times negative 5 is negative 30. And the 2 numbers that multiply to negative 30 and add to negative 1 are negative 6 and positive 5. Negative 6 plus 5 equals negative 1. Check. These 2 values are the ones that you're going to use to split up your middle term. So you're going to rewrite your polynomial as 6t squared minus 6t plus 5t minus 5. So the only thing that's changed is you're now combining like terms, negative 6t, positive 5t, to add to negative t. Just creating this situation where you now have 4 terms and you can factor by grouping. And this works out really nicely for you. And remember, by the way, if you had gotten these in a different order, it's fine. It'll still work out just fine. I kind of like to have the groups have the common number in them, but if you want, I can do it the other way and show you that you'll get the same thing. All right, 6t comes out of the first group. That leaves you with t minus 1. In the second group, you have a 5, and that also leaves you a t minus 1. You're looking for this factor to be common in each set. So what you're left with now is t minus 1 times 6t plus 5. Now remember, you could have said that this was 6t squared plus 5t minus 6t minus 5. If you had combined them in a different order, it's fine. You'll still end up getting the exact same thing. It'll look slightly different when you factor it, but in the end, it'll be the same. So you'll take out a common t here, and that leaves you with 6t plus 5. And then you would take out in the second set a negative 1. Negative 5 divided by negative 1 is positive 5. And then you'll notice that you still have a factor of 6t plus 5 and a factor of t minus 1. So same answer. Does not matter what order you write those middle terms in. So that was number 3. Questions on number 3? Okay. Number 4. So this was solving a polynomial equation. We're going to use that 0 factor property. Now remember, you need the right-hand side to equal 0 in order to use the 0 factor property. If it doesn't equal 0, you're going to have to expand this out and get it set equal to 0. But in this case, as long as you have 0 on the right-hand side, you can take each factor and set it equal to 0. And then solve each one of these equations on its own. You'll get 3 solutions here. Trying to think. I don't think there's one where the right-hand side isn't 0, but this only works because we have a 0 factor property and the right-hand side 0. So if you had something other than 0 here, well, you'd have to expand this whole thing out and subtract it off both sides and then try to refactor it. I did do something similar to that in 6.6 in your notes. It wasn't quite as long as this. It might have just been like this equals some number, but it is in your 6.6 notes. Questions on number 4? Okay. So what followed this was stuff from chapter 7. I'll expand this out. I don't know if you guys were able to get a chance to print this or not, but this will at least give you a good bird's eye view. We went over the stuff from chapter 7 for the domain, simplifying. This was from 8.2. If you guys see something you want to cover, stop me or chat me and tell me what you want to talk about. I mean, we only have 8 minutes left. If you're done, that's fine too. I will post the solutions. These are also from 8.2. Might as well mark that. 8.2. And we did one of each of these in 8.2. We did an absolute value graph, we did a cubic graph, and we did a radical graph with a square root. Okay. This was all stuff from chapter 9. I think I'm going to do 22 A and B just because there were still some people who were struggling with this on the last test with simplifying these radicals, and it is such an important skill. So maybe we should do that. All right, and I love the square root of 48. The reason I love the square root of 48 is because people always screw up the simplification. They always say, oh, well, 4 is a perfect square factor, and then they don't simplify it all the way. You have to choose the largest perfect square factor. And actually, 16 is a factor of 48, and it's a perfect square. So when you're simplifying this, you must choose the largest perfect square factor. And you know what? I'm just going to rewrite this as 2 different factors. So 3 times 16 gets you to 48. Now, as far as the 108 is concerned, you're going to have to, oh yeah, 9. 9's a perfect square factor. We know that 9 times 12. Oh, you know what? 9 is not the largest perfect square factor then. Do you know how I know that? Well, because 12 also contains a perfect square factor of 4. So it must be the case. I bet you it's 36. 108 divided by 36 is 3. So 36 is actually the largest perfect square factor. So just be careful with this, because if you said, oh, cool, I found a perfect square factor, I'm going to go ahead and take it out. Well, if the other factor still contains a perfect square factor, then you still need to keep simplifying. So you'll be making it easier on yourself. I'm going to just leave this so that it's visible. You'll be making it easier on yourself if you find the largest perfect square factor. So 36 times 3 is a better way of simplifying that. Like I said, you'll get to the same answer in the end as long as you realize you still have some work to do there. Okay, so let's simplify this one. So the square root of 16 is 4. So you have 4 times the square root of 3 plus 6 times the square root of 3, which is 10 times the square root of 3. So I just want to make a note that the 12 still contains a perfect square factor. So that was a great problem to do. Any questions on 22A?
I had a quick question. Yeah, can you add the radicals or no?
What do you mean? Like add the radicands?
Yeah, that's what I meant. So like when there's the 3s, you can't add them ever.
Right. So a lot of times students think that this is a property, but it's not. You cannot take the square root of a plus the square root of b and get the square root of a plus b.
Okay.
So we do have that for multiplication. So no, yes. Doesn't work with addition. So yeah, remember that when you're looking at this radical factor on each term, that's really kind of acting like a variable. Like when we combine like terms, that's kind of what's telling you have like radicals, and you just kind of carry it on like you would a variable.
Okay, thank you.
You're welcome. Then let's do B, a little more simplifying. The square root of 8 we can break down into the square root of 2 and the square root of 4. And that is the largest perfect square factor. So you take out the 4 and then can't get any simpler than 2 at that point. And then 9 and 2 for the square root of 18. 9 is a perfect square. Multiply it by 2 and you get to 18. And then we'll simplify. So you'll have 3 times, and then the square root of 4 is 2 times the square root of 2. 5 times the square root of 9 is 3 times the square root of 2. And you have like radicals here, but go ahead and multiply your coefficients. So you'll have 6 times the square root of 2 minus 15 times the square root of 2. And here is where you have the situation where you have like radicals, and you're just going to act like that square root of 2 is just kind of like a variable that you're pulling along in each successive computation. 6 minus 15 is negative 9. So you'll have 6 square roots of 2 minus 15 of them gives you negative 9 of them. And that was 22B. Questions on B? Okay, we have like 3 minutes left. I don't know, anything sticking out to you that you want to cover in 3 minutes?
I had a really quick question. For our final, how many problems do we have?
Well, it's going to be, I mean, I put in my math lab review on there, but it's got to be shorter than that. And the review that I put on there wasn't a test form. It was like a homework form because it seemed silly to me to treat it like preparing for your test, because your test can't possibly be that long. I just wanted to give you a few of each kind of problem. Whereas your test will have, your final exam would have like this one or that one. It wouldn't have both, that sort of thing.
Okay.
I haven't actually written it yet. I have to do that. I haven't actually entered it into my math lab yet. But it's got to be short enough that you can reasonably take it in 2 hours. And I'll probably set it to go from 5 to 7 and just give you the 120 minutes instead of 110. Just, I don't know. I usually would do that in class anyway. But I don't know how many questions. I'm guessing like 30, probably, because that's, how many you would normally see on an exam. And that's probably what would be reasonable to be completed in 2 hours.
Okay. Thank you.
Sorry, I know it's not that helpful, but that's the plan. Just, you'll see something from each section probably. Unless it's a kind of a foo-foo section. Anything else? Okay, well, if you come up with any questions, email me. I'm going to put your test up over the weekend. I'm going to try to remember to make it available for the right date so that no one's confused when the test time starts. And yeah, that's it. I'm going to post these notes that we did in class on our D2L page, but I'm going to also post my smaller key just because, it's like a little bit tighter. Well, this is what I already had done. So you can see how it's just a little bit more crunched. But that's it. Final exam on Tuesday, and you guys are done. So sorry we had to end the semester like this. It really sucks because I'm really going to miss some of you guys. I got to know you so well, and then that was it. Never saw you again. So, but I hope you guys do well on Tuesday, and hopefully we can get back to a regular semester in the fall. But I don't know. Keep in touch. If you have questions, email me. That is all.
Thank you.
Thank you.